Hello everyone, my name is Yuhao and today I'll be talking about single-photon camera guided extreme dynamic range imaging. Traditional cameras have very limited dynamic range. We say dynamic range to denote the ratio between the brightest and the darkest pixel in a given image. I took this photograph of El Capitan during a beautiful sunrise, but unfortunately my camera wasn't able to capture the details in the highlight using a single exposure. By merging multiple images at different exposures, I was able to capture the detail in both the highlight and the shadow. But what if we want to achieve the same dynamic range using only one exposure? You might have heard an emerging type of sensor technology called single-photon cameras. It was recently shown that a single-photon camera can provide extreme dynamic range, well beyond a conventional camera. In particular, SPCs can achieve extreme HDR with just a single exposure, and its dynamic range is even higher than exposure bracketing with two images from a conventional camera. Let's briefly talk about how the single-photon camera achieves HDR. The graph that you see on screen is the sensor response function of a conventional CMOS sensor. You can think of the x-axis as the scene brightness and the y-axis as the number of photons registered by the sensor. When a conventional sensor collects light, the number of photons detected is linear with respect to incident photon flux, resulting in a straight line. However, CMOS sensors are subject to foveal capacity limits, after which they are no longer able to register incoming photons. In contrast, an SPC has a nonlinear sensor response function due to its dead time following each photon arrival event. Therefore, the range of intensity values that the SPC can record is much higher than the conventional camera. Further, SPCs have already found their way into consumer devices. For example, the latest iPhones and iPads have built-in LiDAR modules that use single-photon detector technology. However, one key limitation of SPC is its low spatial resolution. It turns out that it is difficult to manufacture high-resolution single-photon camera arrays. For example, here we only have around 30 kilopixels. Our work is motivated by the fact that current single-photon cameras and conventional cameras have complementary capabilities. A conventional CMOS camera gives you high resolution, low dynamic range, while a single-photon camera gives you low resolution, high dynamic range. It would be great if we could combine data from the two sensors. To do that, we take the raw readouts from the two sensors. For SPC, we extract the detected photon counts and linearize using the inverse of the sensor response function that you saw earlier. Now, the pixel values for both images represent estimated photon flux. We use them as inputs to our fusion network. Here is a diagram of our network architecture. Both the CMOS and SPC inputs are sequentially filtered and downsampled to extract multi-scale features. The sensor fusion decoder further filters and upsamples the feature maps. The last layer applies a blending operation of the CMOS input and the learned upsample features from the SPC image. Now let's take a look at some results. Comparing to super-resolution networks that only use SPC input, our network utilizes high-resolution CMOS data to better retain fine features such as text and does not introduce high-frequency artifacts. Compared to single-image HDR networks that only use CMOS input, our method consistently produces more plausible texture details that closely resemble the appearance of the subject. Comparing to exposure bracketing that uses two CMOS images, our method does not produce noisy image segments with discontinuous signal-to-noise ratio levels. Lastly, our model performs reasonably well with real-world experimental data, as it recovers both dynamic range and scene details better than the baselines. Overall, our SPC-guided HDR model provides a way to achieve extreme HDR imaging with today's single-photon cameras with limited resolution. This will have implications in various applications, including machine vision, autonomous driving, and consumer photography.